Hi, this is Professor Fernandez working on class notes G in lesson 9. This is an example of how to use Cramer's rule to solve a system of linear equations. Let me scroll up a little bit and remind you of what Cramer's rule is. So this is the statement of Cramer's rule. First of all, it is a result that helps you find the solution to a system of linear equations. The assumptions are that you're given the matrix A and you're given the right-hand side vector B. And first of all, this is an existence theorem, and it is also a computational theorem. The existence part tells you that if you know that the coefficient matrix A has a non-zero determinant, then the system has a unique solution, and also vice versa. If it has a unique solution, the determinant is non-zero. But for the purposes of finding a solution, we usually use the first part of that. We calculate the determinant of the coefficient matrix, check that it's non-zero, and then we know we have a unique solution. So if that was it, that would still be a pretty useful result. But Cramer's rule also tells you how to find the solution. So it tells you that the vector x that you're looking for, which has however many components x1 through xn, it tells you that the ith component in here, x sub I, is the determinant of this new matrix A sub I obtained by replacing the ith column of A by the vector B, divided by the determinant of A. So that's one of the nice things about Cramer's rule. It gives you the answers for the components of the unknown vector x in terms of the determinants of A and variance of A. So let's see how all of that works out for the example that we are going to work on in this class notes. So I will erase all this and then scroll back down. Okay, so we'll scroll down here to this example. So first thing we will check, even though it says use Cramer's rule, which assumes that it implies that this is a problem that you can actually apply Cramer's rule to. I'll just check the determinant condition anyway. So first thing we got to do is put this into matrix form. So the right hand side is 10, 15. Remember the left hand side, we pick out the coefficients here, and the coefficients are 1, 1, 1, 2. Okay, so this is our A matrix, this is our B vector, and then let's calculate the determinant of A. Make sure that it's not 0, and then we can use Cramer's rule. So as usual, to take the determinant of a 2 by 2 matrix, multiply the diagonal, and then multiply the off diagonal, and subtract. So this is 1, which is definitely not equal to 0, so Cramer's rule applies. Great. And then I'm going to actually start using Cramer's rule. So the vector x in this problem has 2 components, and that is inherited from the notation in the problem itself up here. So the 2 components are x and y. So the second part of Cramer's rule says that the first component here, x1, is going to be the determinant of a1 over a. And the second component, y, is going to be the determinant of a2 over a. Okay. So let's use all this to calculate these 2 components. So first of all, notice that we already calculated the determinant of a, so that's going to go in the denominator. It happens to be 1, so that's not really going to change much in our calculations. And now let's talk about this determinant of a1 in the numerator. So in Cramer's rule, the numerator determinant is the determinant of the matrix formed by replacing the ith column by the vector b. So a1 means we're going to replace the first column of the matrix A by the vector b, and we are going to keep everything else unchanged. All right, so the first column used to be 1, 1. Oops. First column used to be 1, 1. Now it's going to be 10, 15. So I'm going to put that down here, 10, 15. I won't change the second column, which used to be 1, 2, and it's going to remain 1, 2. Okay, and then from here, I'm actually going to calculate this determinant as usual. So multiply the diagonals, so that is 20. multiply the off diagonals, 15, and then subtract. So that gives me 5. And that's my x value. Great, so I will now do this all over again for y, except, the denominator in y is still determinant of a, which is still 1, so that doesn't change my arithmetic. The numerator now is determinant of a2. So I'm going to go back up to the matrix A, replace the second column, because we're talking A2, with the vector B. So it's going to be 1, 1, and then 10, 15. So I'll put that down here. 1, 1, and 10, 15. Great, and I'll calculate my determinant as usual. So I have 15 minus 10. That also gives me 5. All right, so therefore, Cramer's rule implies that the x and y values that solve this system are both 5. And, this is something that it's such a sophisticated results Cramer's rule that it's sometimes useful to check just to make sure that you've done the arithmetic correctly. There's a lot of stuff going on with the determinants and the a sub 1 and a sub 2. So we can always check our work in a linear system if we think we found a solution by substituting it into the system. And if I put in 5 for x and 5 for y here, I do indeed get 10. Satisfies the first equation. How about the second one? If I put in x equals 5, y equals 5, is that equal to 15? Then yes, that's also true. 10 plus 5 is 15. So we've satisfied both. So we have verified that x equals 5, y equals 5 solves the system.